Then start. So now, like, we will discuss resonance. So the question which we are discussing, it's a PYQ question. What is resonance? Yeah, what is meant by resonance?
Well, I can give it a try. Resonance is when there's when there is oscillatory motion with a given time period, and it repeats. Yeah, okay. It's a very bad explanation, but yeah, something like that.
Yeah. So what is meant by resonance, and also draw the resonance curves. This is the complete question. And what is meant by resonance? Also draw the resonance curves. So this resonance curve is very important.
Hmm.
Taking into account the damping coefficient. So this is what we have to do. So let us understand the meaning of resonance, and also let us understand how to draw the resonance curve.
Hmm.
So see, now the idea is that resonance, basically it is a phenomena which occurs when a system is driven by an external force
Hmm.
at a frequency close to its natural frequency. And when it happens, whenever the resonance occurs, there is always a increase in amplitude of oscillations.
Hmm.
So let me write it properly, whatever I have said.
Hmm.
So when I talk about resonance, so I will say that resonance occurs resonance occurs when a system resonance occurs when a system is driven by an external force.
Hmm.
At a frequency at a frequency close to its natural frequency. So the idea is that we know that there is a natural frequency with which any particle or any system is oscillating
Okay.
naturally,
Hmm.
isn't it?
Yes, sir.
But we can apply an external force, like we can apply an external frequency Now that external frequency we are applying, if it becomes close to the natural frequency, then resonance occurs. So resonance occurs when a system is driven by an external force at a frequency close to its natural frequency.
Uh,
This is the condition for resonance.
okay.
Now, next point, resonance leads to a large increase in the amplitude of oscillations. Resonance leads to a large increase in the amplitude of oscillation, isn't it?
Yes, sir.
So this is the idea.
Mm.
Now it is very clear that resonance occurs only for an oscillatory motion, isn't it?
Mm.
So this also I can, because see, if they're asking about resonance, whatever we know about the resonance, everything we should write.
Mm.
Even the minute detail also we should give to fill the answer with appropriate like points. So first we gave the condition of resonance. Resonance occurs where a system is driven by an external force at a frequency close to the natural frequency. Then only resonance will happen. Whenever resonance happens, resonance leads to a large increase in the amplitude of oscillations. The amplitude automatically it increases because of the resonance.
Mm.
And one more very important point of resonance is that resonance occurs only for oscillatory motions. Resonance occurs only for or resonance occurs in system that exhibit oscillatory behavior.
Mm.
So resonance occurs only in those systems exhibiting resonance occurs only in those systems exhibiting oscillatory behavior.
Mm.
So this is also very important point of resonance.
Mm.
Okay. Now one more very interesting point I can write. Resonance, the phenomena of resonance is highly dependent on damping. And what is damping? Damping is the resistance or friction. And damping dissipates energy and reduces the amplitude of oscillation.
Mm.
Damping to we know, no?
Yeah.
One more point about resonance. resonance is highly dependent on damping. Now let us see what is this damping. Damping is the resistance or the friction damping always dissipates energy. Damping always dissipates energy. And damping reduces the amplitude of oscillation. Oscillations over time, isn't it?
Yes, sir.
So this is the like theoretical aspect of resonance. Like now we got an idea that oh, if I talk about resonance, resonance is a phenomena which will occur only in the systems exhibiting oscillatory behavior. And in order for a oscillatory system to exhibit resonance, there should be an external force at a frequency which should be closer to the natural frequency. And if it happens, we say that resonance occurred. And whenever resonance occurs, there is an increase in amplitude of oscillations. There is an increase in amplitude of oscillation. And resonance is highly dependent on damping. Damping is basically the resistance or friction for the oscillatory motion. Damping always dissipates energy, and damping reduces the amplitude of oscillations over time. Now we will look at the mathematical aspect of resonance. That is very important. Mathematical aspect of resonance. So let us consider a damped harmonic oscillator driven by an external force. So consider a damped. Damped means in this harmonic oscillator, there will be damping will be there. Consider a damped harmonic oscillator. It will undergo oscillatory motion, this harmonic oscillator. So this damped harmonic oscillator, it is driven by an external force. Driven by an external force. That external force, let us write it, mathematical expression of that. Ft is equals to F naught cos omega. So this is the external force, and hence this external force is having a frequency element also.
Mhm.
Here, in this equation, we have omega. We will have an omega naught. We will have a damping coefficient. I will call it DC, damping coefficient. We will have mass and we will have damping factor. So this mu is the driving frequency. Like external force is acting now on the harmonic oscillator, and that external force is being acted with a frequency.
Hmm.
And that frequency is the omega, and we call it the driving frequency.
Acting to support or oppose, like the one which is helping oscillation happen.
Yeah. It depends. It can be any of that.
Okay.
And omega naught is the natural frequency, system's natural. So when this driving frequency becomes close to system's natural frequency, then only resonance will occur. No?
Yeah.
DC is the damping coefficient. M is the mass. And it's the damping factor. It is 2mdc, which is the damping factor. In order to mathematically understand resonance, we will be making use of all these symbols. And we are considering a damped harmonic oscillator which is driven by an external force.
Mhm.
Now, when that harmonic oscillator is driven by an external force, the amplitude of oscillation,
Okay.
let us see that what it will be. Amplitude of oscillation. Capital A is equal to, or I can say A omega. Like A as a function of omega, where omega is the frequency, driving frequency. It
Mm.
is F naught by N.
Mm.
into 1 upon under root of omega naught square minus omega square का square. So this is the difference between the driving frequency and the natural frequency. This will difference will determine the amplitude plus 2 into damping coefficient omega naught square. Isn't it?
Yeah.
Now, whenever you will be discussing the mathematical aspect of resonance, this equation is the key. Because see, what is resonance? Resonance is when the driving frequency becomes close to natural frequency. Let us suppose driving frequency becomes equal to natural frequency, then what will happen? Let us see. Then this term will disappear. When this term will disappear, the denominator will decrease. Because if there is some number here, because of the square, the denominator will increase. And when denominator will increase, amplitude has to decrease. But when this term disappears, the denominator will decrease, and because of which amplitude will increase. Isn't it?
Yeah.
So this proves it.
Is this the derivation?
Yeah, like no derivation, like this formula just you should be aware of. And this is
But I don't
what
think we use this formula often, sir. Do we?
yeah, we will be using it for resonance.
Okay.
This is an important formula.
Okay.
Okay, you have to be aware of this.
Hmm.
Here it is multiplied. Dot means multiplied.
Yeah.
So F naught by M into this. Now see. So here I will say that for the driving frequency approximately equal to the natural frequency. Like theory, you can write the denominator will increase. But straight away result I will write. Amplitude of oscillation will increase. Amplitude of oscillation will increase, isn't it?
Yes, sir.
So this is the idea behind the resonance. And here this damping factor also plays a role. If damping factor increases, the denominator will increase. And if the denominator will increase, amplitude will decrease. So this damping coefficient so I can say one point about this damping coefficient, that damping coefficient so this damping coefficient, it reduces So damping coefficient reduces amplitude of oscillation. And also the sharpness of resonance, isn't it?
Yes, sir.
Now, one more very important, because see, whatever we are discussing now, you just become very aware of that, because question can be twisted. They can ask about damping coefficient. So we know that we should know about that.
Mm-hmm.
So now this damping coefficient, three possibilities are there. The damping coefficient can be greater than one, less than one, or equal to one.
Mm.
So we will discuss all these three conditions. If this damping coefficient it is less than one, then we say the system is under damped. Because less than one means it is less.
Yeah.
And system is under damped, and hence it's good.
Mm.
System is under. Like damping will be less.
Mm.
And if the system is under damped, then what conclusion we can make? Amplitude will be very large at resonance.
Mm.
Because let us suppose, oh, we got a magical formula, like we got a magical technique that if I calculate the natural frequency and if I drive the system with an external force equal to the natural frequency, then I
Mm.
can take amplitude to the next level. But when I did this, I wondered amplitude is not at all increasing to the next level. And I became clueless. But after some research, I found that, oh, damping is also influencing the oscillation. So I have to like minimize the damping in order to get a large amplitude. That's why we have written the point that resonance also depends on damping. Like
Mm.
this condition is necessary that the external frequency should be close to the natural frequency, but damping is also plays a very important. Damping should be less if you want to get a high amplitude. So if the system is under damped, like if the damping coefficient is very less, then for sure we will get a very high amplitude
Mm.
at a resonance. So amplitude of oscillations will be very high.
Mm.
Amplitude of oscillations is very large. At resonance. Isn't it?
Yes, sir.
Okay, this is clear. Now the second possibility this damping coefficient if it becomes equal to 1,
Hmm.
then it is known as critical critically damped system.
Hmm.
Critically damped system.
Sir, is this there in the PDF this much depth?
Yeah.
Okay.
So see, whatever we are discussing, it is of utmost importance
Okay.
because it is clearly mentioned. You have to master natural like free oscillations, damped oscillations, resonance. Everything is there. So whatever we are discussing here, we are discussing about damped oscillations
Hmm.
in the context of resonance.
Hmm.
So here, what will happen in the critically damped system? The system returns to equilibrium without oscillations and resonance is suppressed. So important it is. So in critically damped systems, resonance is suppressed. No resonance will be taken place. Regardless of you make the frequency is equal, the external frequency equal to the natural frequency. If the system is a critically damped system, no resonance will be there. Resonance will be suppressed. Like resonance will be there, but it will be suppressed.
Hmm.
So in a critically damped system, resonance is suppressed. So what will happen is that the system will return to equilibrium without oscillations.
Hmm.
Like without to and fro motion, it will straight away. Once it reaches equilibrium, it will stay there.
Hmm.
It will not undergo any oscillation. So system returns to equilibrium. System returns to equilibrium without oscillations. Without oscillation. So this is the critically damped system.
Hmm.
And we have something called as over damped system. If damping becomes very large, like if the damping coefficient is greater than 1,
Hmm.
then it will be over damping. Over damped system. So in over damped system, what will happen is uh, the system slowly returns to equilibrium without oscillating, and resonance is not at all absorbed, like not at all seen.
Hmm.
In over damped system, resonance not at all occurs. In critically damped system, resonance occurs, but it is suppressed. In
Sir, I
over
got
damped system,
like
yeah,
written
please.
R is damping factor 2M DC, but where is M? M, you mean the one on the outside also? That is what is 2M DC. In the formula, it is 2 DC omega omega naught square, but there damping factor it's M DC. So there is no M in the
No,
M is
no,
out.
no, no, no. This omega, it is the damping factor, but DC is the damping coefficient. So here we are talking about damping coefficient.
So sorry, omega, omega m.
Yeah.
What is m? Where is m? So,
And M is the mass of the system.
but you haven't
No,
mentioned it in the
no,
formula. Like there's one m outside.
yeah. No, but in the formula, we haven't used this damping factor. That we can use it. The how we can use it is we can multiply and divide both the side this by n. I will tell you.
So it just
That
gets
is,
cancelled basically. So it doesn't matter like that.
yeah, yeah. So this I can m square by m square. So this m square, the one it will get inside, it will become m. So 2m dc, I can replace it with the damping factor. Now this m square, it is under root.
Uh,
Now I can take LCM also.
yeah.
So m square will be here, and with this term, and this will cancel. That is also fine. But here we haven't used in this formula, we haven't used this gamma, like damping factor. But see, damping factor is also dependent on this damping coefficient.
Hmm.
So we are directly focusing on that damping coefficient, isn't it?
Yeah.
So we are discussing that. So it is very interesting that in overdamped system, resonance is not at all absorbed.
Hmm.
Observed. So resonance is not observed. It means that, and here what happens is, like experimentally, when we will look at it, we will see that system returns slowly.
Hmm.
System returns slowly to equilibrium
Hmm.
without oscillation. This is the idea. So this was the mathematical aspect of resonance.
Hmm.
Now one more aspect we will discuss, that is the resonance curves. Then we are done.
The
So
diagram.
the diagram, the graph,
Yeah.
that is very important. That also we will discuss. But before that, let us quickly revise very like what we did. So see, when we talk about resonance, the theoretical aspect says that the system should be driven by an external force at a frequency close to the natural frequency. The system should undergo oscillatory motion, and whenever resonance occurs, amplitude increases. But very important point is that resonance also depends on the damping, because damping, it is a resistance of friction to the oscillatory motion. It dissipates the energy, and damping can reduce the amplitude of oscillation over time. So damping plays a very important role. In the mathematical aspect, we considered a harmonic oscillator. It is driven by an external force, uh, with the external frequency omega, like f naught cos omega t. So omega is a driving frequency, omega naught is the natural frequency. And based on that, we have the formula for the amplitude of oscillation. And
Hmm.
we saw that amplitude of oscillation here, if the driving frequency becomes close to or equal to natural frequency, denominator will decrease and amplitude will increase. But also in this equation, we have seen that damping coefficient affects the amplitude.
Hmm.
And we saw that damping coefficient can reduce the amplitude of oscillation and also the sharpness of resonance. So damping coefficient has to be less than 1. Like we should have an underdamped system to achieve large amplitudes
Hmm.
at resonance. But if we have a critically damped system or overdamped system, in critically damped system, resonance is seen, but it is suppressed.
Hmm.
And in overdamped system, resonance is not at all observed. and the system will return slowly to equilibrium.
Hmm.
Now we will discuss the graph, that is the resonance curve. Because this is a PYQ question now,
Yeah.
and it carried good
Uh,
marks.
Sorry, in the PDF resonance is there, like, but I don't. The last, if you go on
No,
the
no,
40,
no. So it is the part of syllabus. Because see, in this resonance, we have to do all this, and if in PYQ they are asking resonance curve, it means it is the part of this.
uh-huh.
Resonance curve is very important. So this resonance curve, what it is, uh, it is also called as amplitude frequency. Amplitude frequency response curve. Resonance curve is also called as amplitude frequency response curves. And what is this resonance curve? Like what is the use of it? What is the significance of it? It shows the relationship between the amplitude of oscillation and the driving frequency for different damping coefficients. So resonance curve show the relationship, like it shows how the by changing the driving frequency, the amplitude is changed for different damping coefficients. So it shows the relationship between the amplitude of oscillations, the relationship between the amplitude of oscillations and the driving frequency. Because for different driving frequencies, we will have different amplitudes. Keeping damping coefficients constant, like different damping coefficients. For different damping coefficients. So this is the idea. Okay.
Hmm.
Now let us draw the graph and analyze it. This resonance curve. Now this is the omega, which is the driving frequency. Let me write it. X-axis is the driving frequency because when we change the driving frequency, amplitude will change.
Hmm.
And we have the amplitude of oscillation. That I can call it A.
Hmm.
Capital A is the amplitude of oscillation. This is basically the we are drawing resonance curves for different damping coefficients. Different damping coefficients. Okay. Now let us make the curve. So three different curves we have to make.
Hmm.
The first one will be something like this, wherein uh, when I increase the driving frequency, the amplitude will increase. It will keep on increasing up to a peak, and then it will fall. Isn't it? Like this is one.
Hmm.
The second one is something like this, wherein only a very small increase I will see, then decrease. And in the third, decrease something. Now, what does it signifies? Let us see. So this blue, it is low damping coefficient. So,
Hmm.
so we know that now, whenever low damping coefficient is low, uh, we will observe the resonance. So,
Ah.
there is a certain driving frequency which is close to the natural frequency, and at that point, we will get the maximum amplitude.
Hmm.
So this blue is the low damping. Like for low damping coefficient, we have this. For medium damping, we have this. For medium damping, some resonance is observed, but it is suppressed,
Hmm.
isn't it?
Yes, sir.
Or to be more precise, let us give it a formal name. So the formal name is underdamped, critically damped, and overdamped.
Overdamped. Heavy damp. Yeah.
So this is underdamped.
Soft closing doors are
Yeah. So
oh,
they are overdamped,
overdamped. Okay.
underdamped, critically damped.
Critically damped are the suspensions, right? On the
Yeah,
bike.
yeah, we can see. In critically damped, resonance is observed, but it is suppressed.
Hmm.
And in overdamped, no resonance at all. Overdamped, no resonance, isn't it?
Yes, sir.
So this is the idea.
Hmm.
Yeah, so it is like easy only, like
Hmm.
conceptual. So whatever we discussed, now I hope you got a conceptual clarity.
Yes, sir.
This mathematical aspect, this formula, and this how this amplitude is dependent on damping coefficient, and this resonance curve explains that.
Hmm.
So this is what needs to be done.
Hmm. Sir, I'll be back in 3 minutes.
Just okay, I have ended the stream.
Oh,
Yeah,
okay.
take your